Good afternoon, everyone. So today, welcome to my YouTube channel, Avatarm. So today we'll see an alternative definition of uniform continuity. Okay. So what is that definition? Definition is that so we are saying that F is uniformly continuous if and only given any epsilon greater than 0, there existed delta greater than 0 such that absolute value of fx minus fy is less than equal to epsilon for all xy belongs to I, with x and y absolute value is less than equal to delta. If you see when I define uniform continuity, how I define the definition. So let's start today's lecture. I have already taught this topic. So what is uniform continuity definition? Okay. Let I subset of R, I is interval. Okay. A function fi to R is said to be uniformly continuous on I if given any epsilon greater than 0, there exists delta greater than 0 such that this is symbol of there exists. The meaning of this symbol, it means that there exists such that fx minus fy is less than epsilon for all x, y belongs to I with x minus y less than delta. Okay. Okay. And we know that every uniformly if f is I to R uniformly continuous, then every uniformly continuous function is continuous. This implies f I to R is continuous. Okay. Every uniformly continuous function is continuous. Okay. Okay. Now we are to show one alternative form of definition which I have written in title. Okay, in first page of this lecture. So to prove that we need some concept. So what is Archimedean property of real numbers? Archimedean property of real numbers. One minute. Archimedean property of real numbers. What is Archimedean property of real numbers? What is this property? Let A and B belongs to real number. Okay. Such that A is positive. then there exists a natural number n belongs to n such that b is strictly less than na. This is called property of Archimedean property of real numbers. Now, okay. Now, corollary, we can write its corollary. Let A and B belongs to R such that A is positive and B is also positive. Then there exists, because A and B are real numbers, both are positive. But in Archimedean property, I need only one. But there are two. Then there exists N1 and 2 belongs to two natural numbers such that that B is strictly less than N1A and A is strictly less than N2B. So it is easy to verify that. So we have this corollary. Why we have this corollary? Suppose we can apply this. We can prove this easily. How? Suppose you see Archimedean property of real numbers. If first time A is positive, then I can simply apply Archimedean property. I will get B is strictly less than N1A. Now what I will do, I will consider B as A and A is equal to B. B is equal to A. Then again by applying Archimedean property, I will get A is strictly less than N2B. Okay. Because in Archimedean property, I need a number that is positive. So when I am proving this corollary, I am taking A greater than 0 as it is in Archimedean property. When I am seeing that B is also positive, I will take B as A in Archimedean property and then I will get N2. Okay. Now I am going to prove my main result. Let's say it's theorem. F I to R is uniformly continuous if and only if given any epsilon greater than 0, there exists delta greater than 0 such that fx minus fy, okay, is less than equal to epsilon for all xy belongs to I with x minus y less than equal to delta. Okay. So if we can prove this, then in the definition of uniform continuity, we can take this definition. Given any epsilon greater than 0, there exists a delta greater than 0 such that this happens. Okay. Proof. Okay. So first, assume that F is uniformly continuous on I. Okay. F is uniformly continuous on I. So let epsilon greater than 0. Since F is uniformly continuous, there exists delta greater than 0 such that Fx minus Fy less than epsilon for all xy belongs to I with their difference than delta. Okay. Now let xy belongs to I with x minus y less than equal to delta. Okay. Okay. Now we can find two sequences xn and yn. Both are in I with xn minus yn is strictly less than delta, and xn converts to x, yn converts to y. We can always find. In any, suppose you take any real number on a real line, you always have such sequences, okay, which will have this property, this I, okay. Then F is continuous. This implies Fxn converts to Fx, okay. Fyn converts to Fy, okay. So let's see it equation number 1, this equation. Let's see this equation number 1. From 1, because since xn minus yn difference is less than delta, we have from equation number 1 that Fxn minus Fyn will be less than epsilon, okay. So letting and tending to infinity, we get what we will get, because xn will convert to fx, okay, and yn will be convert to yn. But when a sequence converts, it can be equal also. Suppose a sequence you take 1 minus 1 upon n. This sequence is always greater than this sequence is always less than 1. But when n tends to infinity, its limit becomes 1. So when sequence tends to limit, the limit things can be equal also. Okay. That is why we have to write here less than equal to. Okay. So what we got? We got fx minus fy is less than equal to epsilon for all xy belongs to I with x minus y less than delta, less than equal to delta. Okay. Because we have also checked those points which difference is x minus y is equal to delta. So they can be equal also. And if x minus y is strictly less than delta, they will be fx minus fy less than, strictly less than epsilon. Okay. So this inequality is satisfied. They can be equal to epsilon, and their difference can be, image difference can be strictly less than as well. Okay. So so 1 implies 2 is done. It means one direction is done. Okay. Conversely, assume that given any epsilon greater than 0, there exists delta greater than 0 such that fx minus fy is less than epsilon, less than equal to epsilon for all xy belongs to I with x minus y less than equal to delta. We have assumed convergence statement. Now we are to show that f is uniformly continuous on I. Okay, we have to show this. So what we will do? So let epsilon greater than 0 take, so now 1 is greater than 0 and epsilon is greater than 0. By Archimedean property of real numbers, there exists n belongs to natural number such that 1 is still less than n epsilon. Okay. So what does it mean? It means that 1 upon n is less than epsilon. This means 0 is still less than 1 upon 1 by epsilon. Okay. Now we put epsilon dash is equal to, so this is positive. Now we can take my epsilon is equal to epsilon dash. I will apply the converge statement I have assumed. I will apply that converge statement for epsilon dash. Okay. Now by assumption means we have taken converge statement. By assumption, there exists delta greater than 0 such that fx minus fy less than equal to epsilon dash for all xy belongs to I with x minus y is less than equal to delta. Okay. Okay. Now take xy belongs to I with x minus y less than delta. So obviously this condition x minus y, this condition is satisfied because once you have x minus y value, absolute value is less than delta, obviously this condition is satisfied. What is this condition? Their difference should be less than equal to delta. Once they are different, what are those xy which either their difference either equal to delta or is strictly less than? We have strictly less than, so this condition is satisfied. Okay. So by this, so we will have what we will have by this equation number 2. From equation number 2, we have what we have. We will have fx minus fy less than epsilon dash. But epsilon dash is 1 minus 1 upon n, and this is strictly less than epsilon. Okay. So this implies fx minus fy is less than epsilon. So we got what we got, fx minus fy less than delta for all xy belongs to I with x minus y less than delta. Okay. So what does it mean? It means f is uniformly continuous. F is uniformly continuous on I. So this theorem is done. So it means in the definition of uniform continuity, we can take this definition. We can take this definition. In the definition of uniform continuity, we can this definition. Given any epsilon there, given any epsilon greater than 0, there exists delta greater than 0. You can take absolute value fx minus fy less than equal to epsilon. In the definition of uniform quantity, we have taken strictly less than. And here, in place of this, we can also take less than equal to as well. But in definition of uniform quantity, we have taken it strictly less than also. Both the things can be taken less than equal to, okay, in place of strictly less than in the definition of uniform quantity. So today's session up to this, I have shown equivalent form of definition. So if you have any problem related to this session, you can comment on my YouTube channel, and we will see it in next session. So kindly like, share, comment, and subscribe my YouTube channel. Thank you very much for today's session. Thank you very much.